Good morning, everyone. Can you hear me?
Good morning. Yeah. Good morning. And yes.
Okay. My Zoom page, I can find you again. Okay. Can you see my screen?
Yes. Yeah.
Okay. All right. I want to hope that we had a good time over the weekend and we enjoyed the test. I'm already going through our script. We did well. Okay. So today we want to quickly look at lecture 6. So we'll have a lot to cover because the lecture 6 is just going to be one day. So I'm going to give you just a little percentage of all you have to know on lecture 6 and expect that you will read some of the read up that I'll give to you and you also do the assignments. Okay. So while quickly looking at uniform circular motion, when I was putting it up, I omitted the uniform there. So it's uniform circular motion, orbits, and gravity. So that's what we'll be looking at today. So we just have one day to run through the whole of chapter 6 of our test. Okay, so by next week, we'll move to rotational motion, which is the week 7, and then we'll be handling some of the concepts also that we have learned in the previous lectures. Now, the reason being that we'll have 1 week off the schedule. So if we don't go this way, we'll be at the end of the day missing about 3 lectures, which is not going to help us in the next semester because whatever we are learning this term and this first semester will also apply in the second one, which will be a progress of what we are doing now. Okay, so we have looked at the concept of uniform circular motion before. And then it's coming up here again because we want to advance a bit to add additional information to our existing knowledge about uniform motion. When we say uniform motion, some keywords should come to our mind. Keywords like steady speed or constant speed. We know the acceleration of uniform motion. It states, but when we talk about uniform circular motion, we're talking about the same concept, but the direction of this course is different. Because we have looked at uniform motion before on a plane, like on a straight line, but now we want to look at it in circular motion. How does it differ? What is the new information about the uniform motion of circular motion and that of a straight line? Okay. For circular uniform motion, we have to keep some key points in mind because this lecture is more of bringing out the key points in the whole chapter so that we just have them at our fingertips while we brush up with the read-ups that we'll be having. Okay, so we already established before in our previous discourse that circular motion is a motion of object moving in circle, and the acceleration is directed towards the center of the circle. That is the state of every circular motion. Acceleration is always directed towards the center of the circle. And worthy of note is the net force of that kind of setting. So the net force must also be in the same direction as the direction of acceleration, that is towards the center. So we'll have the acceleration directed towards the center, and we'll also have the net force directed towards the center. So whenever we mention uniform circular motion, it implies that we are saying it's a motion with constant speed, but changing velocity. Okay. Now, this is where it differs from that of motion on a straight line. The reason why the speed can be constant or steady, but the velocity is changing, is because in a circular motion, the direction of the velocity keeps changing. And because the direction is changing, we have changing velocity as well. Let's say we have the circular motion. We know that acceleration is directed toward the center, and velocity direction is a tangential connection to the edge of that circle. So this is our A, and this is our V, meaning that at this point, as acceleration goes to the center, the direction of velocity also changes. So for circular motion, we see that the direction of velocity keeps changing. Uniform circular motion, therefore, tells us that speed is steady, but will have always changing velocity, okay? And then we'll have the operation of the centripetal acceleration, which we said is A equal to V squared over R. This is the acceleration for circular motion. We established that in our last class, and we're also going to use that concept in the discourse of uniform circular motion. Because the motion is circular, the acceleration is directed towards center, and its acceleration is given as the V squared over R, R being the radius of that circle, okay? So let's quickly look at some other concepts that will help us to further understand some of the things we are going to be looking at once we advance into the discussion of orbits and gravity. This term that the period, frequency, and speed. Now, the definition of what we know period, frequency, and speed to be did not change, okay? We know what period is. Period is represented with the letter capital T, and it simply means that time to complete one revolution. That is the time to go round the complete circle, the time it takes to go around the complete circle. While the frequency with the symbol F is the number of revolution per second, okay? How many times can we go around the circle in 1 second? So we have that T and F, that is period and frequency, they are related with this formula, F equal to 1 over T. And this formula is not strange to us. It's just a reminder of what we already know and how we apply it to the study of motion, okay? In this case, it's applicable to the study of motion in a circular direction, all right? So we have that the unit for frequency is in seconds, that is per second, because T is measured in seconds, so we have the seconds raised to power minus there. which is also recognized as the hertz for frequency. Okay. So now that we know the period, we know the frequency. How are they related to velocity? How do we bring it to the description of an object in motion? We know already the definition of speed, which talks about the change in distance per time. And then we know the definition of velocity, which is the change in speed per time. Now, if we have established that the motion of the object is circular, this distance around the circle, as we have seen in one of our assignments, the circumference of this circle is 2 pi r. So to define this distance, if an object should travel around, then come back to this position, the distance it covered is 2 pi r per time t, or the period, because we have defined period to be time taken to complete one revolution. So that is how we came about this formula of the velocity for objects taking one revolution. So the speed v for one revolution is given as v equal to 2 pi r over t. So you see that we did not just import 2 pi r into the equation, okay? So it came from our understanding of existing concept. So this therefore gives us the relationship between the speed, the time, and also the frequency. Because we know that f is already 1 over t. Therefore, we can actually put f into this equation, and it will become this, because it's going to be v equal to 2 pi r dot 1 over t. That is the meaning of that equation. So if you replace this with f, it gives you this equation. So this particular equation shows the relationship between v and t and v and f. That is the relationship between velocity, speed, frequency, and period. Okay, so that is how we describe the speed of an object taking a circular path. You should take note of this formula, okay? So, but we have already established in our previous lectures, as stated here, that acceleration of an object in a circular path is a equal to v squared over r. That means if we substitute this value of v into this, we'll have this squared. Because of the r here, it's going to take care of, if you have 2 pi f r squared, and there's an r at the base, so you will have 2 pi f, you know, 1 r will take care of 1 r. Okay, so what you have left is 2 pi f squared, which is frequency, then r. All right, so acceleration therefore is equal to 2 pi r squared, 2 pi f squared r. And if we bring in the period as well into the expression, we are going to have it this way. So whether we are expressing acceleration in terms of frequency or period, we are going to have the 2 pi r, the 2 pi squared r. Okay, so it's either going to be f or 1 over t. And the application of this whole equation can be clearly seen in example 6.2 and 6.3 of our test. Now, the reason why we did not have to look at the example is if we're to be taking this discussion for the week, we'll look at several examples of the formula we see or discuss. So that's why I put it here, study example 6.2 and 6.3, and I expect you to do that. Okay. You will also see it in your assignment, what you'll be doing about the examples. But when you go through the example, because we did not discuss it in class, and you have any question, feel free to send me a mail about it, okay? Or ask a question. You can send me a mail, drop a chat on the module, and whatever means of communication we have, just use them, all right? So let's advance to the next discussion, which is the dynamics of uniform circular motion. Whenever we encounter the word dynamics, I want a part of you to also ring kinematics, okay? Because there's no way we'll be talking about dynamics of motion without importing our own understanding of the kinematics which describe motion without the force. But in terms of dynamics, we want to actually talk about the forces that actually bring about the uniform circular motion. What force actually drives the object to the center of that circle? That's what I want to look at. So, but what you have noted under this discourse is that particles in circular motion at constant speed have net force, as we see in Newton's second law. This is an established law that we can always import, okay? And because we already know that the acceleration of a circular motion is, you know how many times you have seen this formula today? V squared. If you put that into this equation, MA, we are going to have this value, mv squared over r, okay? So we see how that the second law was used to transform that equation to what it is, all right? So this particular equation is a net force producing the centripetal acceleration of uniform motion, all right? So whenever we look at the dynamics of circular motion, we're going to always call back this equation to mind that brings about this acceleration, which we have stated that the acceleration and the net force will have the same direction towards the center of the circle. Now, the free body diagram of the uniform motion, because what we have just discussed on this point is something you already know, it's not new, but this is the new part of this discourse, that the free body diagram is always having its x-axis directed towards the center. For this to obey the Newton's second law, it has to always, not the word always, directed towards the center. So if you have a circle and, you know, at this point, the acceleration is going to be pointing this way, it appears like this is the direction of y-axis, right? But we are saying that whenever you want to describe or draw the free body diagram for objects in a circular motion, you have to make, because it's always changing, you have to define that part that is going towards the center as the x-axis. Okay, so if we have something like this, we are going to call this the x-axis, and this will be the y-axis. Yes, it's against the horizontal and vertical, but look at it as a circle, meaning if you roll this circle or move it, it's going to take that shape, the horizontal and the vertical that you know. So not just the description of, in this case, we're not just describing axis in terms of the y-axis is the vertical, the horizontal is the s-axis. No, what defines our s and y-axis is the direction towards the center pattern. We're making sure that the x-axis is pointing towards the center. That way we can apply our Newton second law to solving the problem. Having stated that, it means the component description for this law is going to be, because there will be nothing really on the x as on the y axis at the tangent, which points the velocity or that direction is not, well, it depends on the direction of the object. Okay. So the component expression of the net force for x-axis will be equal to the acceleration. We already know this fact. But for the y-axis, we have no force in that direction. So it's going to be 0. Okay. So for the description in terms of making our free body diagram, we will see that we'll have the net force or summation of forces on y-axis to be 0, and that for x-axis we have value. And this we have also emphasized in example 6.6 and 6.8. And I expect you to look at each, because each subject or topic we discuss under this broad topic, uniform circular motion and orbit and gravity, we are taking two examples on that. This is how it ought to be, but I'm going to leave you to go through the example while I explain the concept behind those examples. Okay. All right, so let's look at another one, which is apparent force in circular motion. Now, we have seen this word apparent before in our previous class, and we saw it when we discussed apparent weight. And we said something about apparent weight, right? Which we describe as WAPP, to stand for apparent weight, is equal to the sum of the contact force around that object, which gives you the feeling of lightness or heaviness during motion. Okay, so we are going to import that idea of apparent into describing apparent forces in circular motion. Now, we know that apparent weight, they are not real. Whenever we use the word apparent to describe any concept, we are talking about the feeling which we kind of believe is real, but in essence, it's not, or in principle, it's not real. Okay, so for object moving in a circular path, whenever you make a swing or a car is taking a curve, whatever motion that is taking the curve or circular path, you have this feeling like a force is pushing you outward. Let's take this regular example of the car making a curve on maybe the car is driving on, not say too high speed, but at least the speed that you can feel, and it's taking that curve with that speed. You feel like you're having a push or being flinged towards the door or outward. Okay, you feel like you're experiencing a force that is pushing you outward. We have this word centrifugal force to describe forces that seems to push you outward from the center of a circle. This force is what we are referring to or looking at as apparent force. Why? Because despite it has the name centrifugal force, which can use to describe the direction of a force that is taking you outward from the center of the circle, we have already established in principle that any object moving or taking a circular path has acceleration directed towards the center. And the question is, why are we not, instead of when we are taking the circular path, being pushed to the center, since that is the direction of acceleration? That is why we want to look at what we call apparent force. That force is not real. Despite its name, we have its concept. It is a feeling, just like the apparent weight we've seen earlier. What is actually happening to your body when you experience that is that your body, let's take like you're taking a curve. At this tangent, you see the velocity is going like this, acceleration is going like this. Your body is actually trying to keep a straight motion, that is moving a straight line, but it's being forced to take that curve by that force. So you're experiencing a feeling that is as if it's pushing you to the end, but actually it is that push that helps you take that curve so that the acceleration can be towards the center, because you're not going to go off the car. The car is taking the curve, but the object is feeling like I'm being pushed away from the center, but it's making that curve round, and acceleration is now directed towards the center. And that's what we're describing here. That what your body is feeling is trying to move ahead in a straight line, which would take you away from the center of that circle, as if you are going to the outward, but the door of that car will turn you back into the circle. So you successfully make the circular turn with the car. And if we are to analyze your acceleration, it's going to be actually centripetal. It's going to be directed towards the center. Okay. So one thing about this force, because it's apparent, it's not real, we do not include it in free body diagram. Okay. So for free body diagram representation of forces for circular motion, we do not consider the apparent force because it's not real, it never appears. So we don't consider it. So let's take an example, looking at the roller coaster motion in this case, and we want to use this to describe the apparent weight in circular motion and also see how the apparent forces came into play in the description of our free body diagram. Okay, so look at this roller coaster. See them inside when they're moving at the base and at the top. They will have different feeling of apparent weight. Remember when we discussed about when you're taking a lift, when you feel light, and then when you're coming down and you feel heavier, that is when apparent weight is greater than the normal weight, and when apparent weight is less than the normal weight. That is what you experience. So for when they are at the top, at this position, we see the free body diagram description. We see that in this case, look at the direction of the normal force. That is why when we were describing the direction of normal force, we did not just say it points upward, because every motion kind of vary in their description of the normal force. Okay, so we see the normal force here pointing down and the weight also pointing down. Then the net force is pointing down. So this down motion, which is towards the center, is regarded as the S-axis. And that's why we said we should always make the direction of S-axis to point towards the center. But when they were at the bottom, the normal force points upward, the weight points down, and the net force points towards the center, which is the direction of the acceleration. So we see that the apparent weight for a circular motion, the apparent weight is equal to the normal force. Remember the definition of apparent weight, which is the summation of the contact forces for an object in motion. All right. So if, having established that, we want to see the net force as regards because we've already established that the y component of this force or circular motion as it applies to Newton's second law is 0. So that is why you'll be seeing us writing only the S component expression, all right, which is the summation of the forces, net force acting on the system. Can only point out 2, which is the normal, the contact force, and the long range force, the weight. Okay, so we'll have the sum of both. The normal is positive for this description, then the weight. And we know that force is equal to MA, A equal to V squared. So that's how we got this. So normal, equating the summation of this force with the Newton's second law, we'll have N minus W, N being the normal force, and that's equated to MA. So we'll have just an equation that is like this, okay? That's the part we are taking, because this first part is the description of its components, and then we'll apply the value for the components. So if we move this across, the sign of equality, it becomes plus. So N will be, because we have already established that the apparent weight is equal to the normal force, and we have N now equal to W plus mv squared. So we can substitute that for N here, which will give us apparent weight is actually equal to W plus mv squared R. So this formula also is what you should note, because that is what we applied also in example 6.9. Okay, so let's quickly move to another concept we want to look at today, which is the circular orbit and weightlessness. We have seen weightlessness before, so we're not going to really dwell on weightlessness. We know that weightlessness does not mean a state of no weight. It simply means the description of the weight of a system where there's absence of apparent weight, no contact force is felt, okay? So the concept of orbital motion is also like the concept of the projectile motion that we saw in our previous discourse for objects that are very close to the Earth. Now we have objects that are kind of a wider distance from the Earth. How do we describe their orbital motion or the projectile motion? It is the description of the projectile motion of objects that are very far from the Earth that gave us the concept of orbital motion. And we know that before Newton came up with the laws, the several Newton laws, he was studying making several experiments, and then we learned also in the experiment of the astronauts in the moon when they dropped the hammer and the feather, and we established that for objects under free fall or taking orbital paths, projectile paths, which is the motion of objects under free fall, the masses are not the masses, the weight. It's not dependent on their motion. And we established that we have their magnitudes to be G, okay? So all those concepts is what we're going to apply to the description of orbital motion. Note, we have established that orbital motion is actually the description of projectile motion for objects that are far from the surface of the Earth. What we describe as projectile motion for objects that are close to the Earth. Okay, so let's look at the example here of the description of projecting an object from the height h to the planet. So let's assume that we launch this object at increasing speeds from the height h, and also saying that there's no air resistance, okay? So we'll have the first object launched at a certain speed, initial speed of A. We'll have the object B, C, and D. When the object was launched, we'll also have, because it's very far from the Earth, the curved nature of the Earth will come to play, or that planet will come to play. So if it's close to the Earth, it's going to be projected like an object on a flat surface. But we know that the Earth is not flat. When an object is very far from the Earth, it will be able to see the curved part or curved nature of the Earth. So if the curve is, if the object is projected and it's going, that the gravitational pull from the Earth is pulling it towards itself, that curve, this curved nature is going to influence that motion as well. All right. So project this at a certain speed. It took the projectile path, landed there. Increasing the speed for another same object, it took the projectile path, and the curved edge is more visible for that longer projection. Okay. So we'll see the ground is curving away from the projectile. So it's moving, taking that path and landed here. So when you now increase the projection or the speed of projecting that object, you see that object C and object B taking about the same curve path. We see the ground curving away from the projectile before the object will hit the planet or the ground. Now, you project at a certain velocity, which we will see later. You see that that object D just keeps going round until it gets, its path is now parallel to the curve of that planet. So it ends up going back to where it started. It never hits the Earth. That trajectory is what describes what we call the orbit. So it takes a path that is parallel to the curved part of the planet. So we see that the projectile force of the object D all the way around the planet, taking, like I said, the parallel path, they never meet with the curvature of the Earth. So its trajectory is parallel to the curvature of that planet. Now, what is this experiment trying to give us? It gave us that description that at a certain velocity, for an object that is far from the Earth, we're going to have the projectile motion that will give us a parallel motion to the curvature of the Earth, such that the description of its motion around the Earth is described with the word orbit. So we have its orbital motion. Okay. So we now establish that the trajectory around the planet or star is called orbit, which is this object D. The state where it moves around the parallel motion to the curvature, but never is but at a certain defined distance. All right. So that's the concept of orbit. So whenever you want to picture the concept of orbit, picture it in direction to with your understanding of projectile motion. So the most important point of this qualitative analysis is that the absence of air resistance, the orbiting projectile is in free fall. So the description of its motion is in free fall. So all the laws that we've studied about free fall applies in this case. Okay, and the only force acting on that object is the force of the gravitational pull, which will be seen later in the Newton's law of gravity. The gravitational pull of the object, of the planet on that object. Okay, because it is actually the gravitational pull that gave it the trajectory it took, which we now describe as the orbit. So it's always under the influence of gravity, but it never gets close to the Earth's surface. Okay. So we see that it's a projectile motion, it's taking the circular curve, therefore the acceleration, weight, net force is pointing towards the center. Now, we already know from Newton's second law that to get the acceleration, because this is just how we were able to establish that G is equal to A. If we're describing it in terms of weight, which is the gravitational pull on it, and mass, we take care of mass, we'll have G equal to A. All right, so the description of the acceleration for objects that is under the influence of gravitational force alone is G. Okay. So this is not an example, it's just to buttress what I was saying about the orbital speed that we'll see later. So an object moving in a circle of radius r at the speed that we'll call the orbital speed will have its centripetal acceleration towards the center. And having established that the formula for acceleration in a circular path is v squared over r, that means that the velocity of the orbit over r, which is equal to g, as we have seen in the formula we just shown earlier about how a became g. Therefore, if we want to make v the subject of formula, making v the subject of formula in this case, this is equal to this, so we're just taking just this part, okay? So if you have v orbital square over r equal to g, make the subject of formula, cross this, and then take the square root. We'll have the orbital velocity of, sorry, please. We'll have the orbital velocity to be equal to roots acceleration under the influence of gravity, the product of acceleration and the radius, okay? If an object does not have this velocity, it's going to have an elliptical motion instead of a circular motion, or a motion that can actually be described as the circular orbit, okay? So the object has to have this speed to follow a circular orbit. But we'll have cases where objects don't have up to exact speed and they give us elliptical motion or elliptical orbits. That is, orbits that are not a perfect circle or that cannot be described approximately as a circle. So with the understanding of this velocity, we can actually calculate the orbital speed of a projectile for other planets, okay? So we'll know that these are constant. The radius of the Earth is represented with, instead of a small r, big R, which will be seen in the formula so under Newton's laws of gravity. So am I going too fast? Because like I'm talking to myself.
No, you're good.
Okay.
Okay, okay. So since we know that this is the value of the Earth, impute that value into this formula, we'll have this expression. G, the magnitude of G is 9.8. The value of the Earth will give us 7,900 meters per second, which when converted to mile per hour give us that value, okay? So we can use this idea to calculate the period of satellite orbit. And this was modified as this. We know how the modification came in. We already know these formulas. We just substituted what V is. And then we got this. If you look at the formula very well, you see that there's no magic in it. We just substituted the values we know for what V is into the relationship of the V equation. All right. So let's look at, now when you read the test, there's a comment about this case applying directly and the description of the orbit of the moon. We said that when we apply that directly to the orbit of the moon, it's going to give us the period will just give us 11 hours, which we know in reality is not true. So what actually happened in the variation of the calculation for orbit of the moon is actually factoring the distance of the moon and the Earth in relation to just those two, okay? So having known what the definition of orbit is, which is a trajectory that forms a parallel motion to the curvature of the planet, okay? I want to quickly look at certain things about orbit of the moon. The moon, we already know, is revolving around the Earth, orbiting around the Earth in approximately circular path, and the force of gravity from the Earth is what is pulling the moon towards it. And we also know that the size of G, that is the magnitude of that pull. Remember, we established that the magnitude 9.8 is actually the magnitude of G for the Earth. When you go to other planets, it varies. Okay, so, but the issue, because that was why I said that when we try to use the direct application of using the orbital velocity to calculate the orbit or the satellite orbit of the moon around the Earth, it will just give us 11 hours when we know that it actually takes about 28 days for the moon to revolve around. So it actually brought into bear the concept of the size of G, that is the size of the magnitude, the gravitational pull, which is seen experimentally and established to be diminishing with increase of distance from the Earth. Okay, so it's actually this understanding that gave us what to be looking at as the law, Newton's law of gravity. So it means that the distance actually influences the magnitude of the pull of object towards the center. All right. Now, every object on the Earth have pull towards one another. Now, the reason why we don't feel it is because it's the pull is not strong enough for us to feel or for us to describe. But actually, the experiment shows that when the pull of an object, a larger object, when it's big enough compared to a smaller one, it can be felt, just like the moon and the Earth, the sun and the planetary bodies. Okay, so Newton, from the observation of free fall when apple dropped upon his head, and he started pondering and trying to understand what actually made, why didn't that apple go up? It's in the air. Why didn't it just fly upward? Why was it coming down? And he came up with the concept of gravity. And he also established the fact that gravity is a universal force. Okay? It was Newton that also told us that every force of objects on the surface have a pull towards each other. But because the masses are not are approximately close, we don't feel it. But when the masses are very wide apart, it can be felt like that of the Earth to an object, any object on it. Okay, so it's a universal force that affects all objects in the universe. Now, it pointed expressly two important things about the law of gravity that I want to look at. The first one is that the force, when we talk about force here, we're talking about that pull, the gravitational pull on an object, all right? The force is inversely proportional to the square of the distance between the objects and directly proportional to the product of the masses of two objects. Now, if you look at these two masses here, we see the bigger one and the smaller one, they have pull towards each other from the center, all right? And whenever we say the distance between them, we're talking about the measurement from the center of this mass to the center of this mass. And we'll have the force of 1 on 2 pulling this way, the force of 2 pulling this way. This one is directed towards the center here. This one is directing towards the center here. All right. So this kind of bring in the action-reaction pair. So in the description of the Newton law of gravity, we're bringing in both the second law and action-reaction pair. Okay. So therefore, we want to define the Newton law of gravity as the law that states that if two objects with masses m1 and m2 are a distance r apart, the object exerts attractive force on each other with the magnitude F equal to m1, m2 over r. Now, this is just the summation of this statement. So The force is directly proportional to the product of their masses. That is the point 2, to the product of their masses, and inversely proportional to the square of their distance, which is r. Then G is the constant of proportionality. And that constant of proportionality is called the gravitational constant. Okay? And it has a standard value. So if by chance we have to apply it to an equation, it will be given to us in a formula sheet as the constant we'll be using. Okay? We have just 3 minutes. Okay, we'll have just one slide also. So we look at, please take note of this. If you define this in words without writing the formula, you just give half answer, okay? And when you write the formula, you also have to define how that G came into play and what G stands for. So let's look at the concluding part of our discourse today. So we have seen that how circular motion, orbit, is described as a circular motion, and the role of gravity also in the production of orbit. The velocity, the acceleration, but still within velocity acceleration, a description of directional motions, okay? So whenever I talk about gravity and orbit, the quickest example is the solar system, okay? Which have all the planets orbiting around the sun. That means the sun is having a kind of gravitational pull of all planets around itself, such that at the speed such that the motion of these planets are parallel to the curvature of the sun. Okay, so that is the meaning of orbit. The motion is parallel to the curvature of that planet around it to produce that orbit, and it's moving at the velocity that is called the orbital velocity. Okay, so we have the planet, close planet, and the far planet. Now let's look at this diagram quickly. We see, let's assume that this is the Earth and this is the sun. We are now establishing that from the definition of Newton's law of gravity, that tells us that the product of these objects, both of them have pull towards each other, right? But it is the gravitational pull of the sun that keeps the Earth orbiting around it. So we want to apply this to give us this equation here. All right, this equation that we'll put in that statement. So from the Newton law of gravity, stating that the product of the mass and then inversely proportional to the root of the distance, which is the distance between this and this, the centers. We know that from Newton's second law, M equals to F equals to MA. So if F is equal to this and F is equal to this, that means we can equate these two. All right. And if we equate these two and define A for circular parts, it means we can actually equate GM M over R squared equal to MV squared over R. So if we make V the subject of formula in this case, that is what we'll get this. Okay. So we see how we are equating this concept, because when we just write it straight, we may not know that we're actually equating those concepts. Okay. So from this, let's make V the subject of formula. We'll see first, we'll try to make this as a straight line. We'll have something like this being equal to this squared, right? So if you bring these two under, you'll have GM M over M, no, sorry, not V. r squared. But there's r here. So this r will take care of one r. This m will take care of the small m. So the big M will remain, which will become G. Remember, it is V squared. So take the square root, you have V equal to the square. So that is how we arrived at this. So for gravity and orbit, this is the speed of the satellite in the circular path and circular orbit of radius r for stars and planets. So we have seen the expression of V in two cases. All right. We saw it the first time and we're establishing it here again. Okay. So whenever you see in your test when an equation is written like this and it was not explained out, try to call back the understanding of your previous discourse. You will know how those equations came to be. They are not magic. Okay. So having established that V is equal to the root of the gravitational constant, the mass of the sun or the bigger planet, the root of the product of gravitational constant and the mass of the bigger planet and the distance apart as V, we can actually, you know how we got this equating V? Remember the very first definition for an object in circular path. This is the circumference of a circle over change in time period. Okay, so if we equate these two and make T the subject of formula, that's how we arrived at this equation. And this is actually the relationship between the period and the radius. And whenever you see period, you can always bring in frequency because the twist of the question can be period and frequency. Okay, that's about the end of our class. The same thing happened here, equating MF to get this. So I'd like you to do an exercise on how we arrived at this from what formula did we impute into this to get this. We actually equated that place where we derived A using the Newton's second law. But this description also followed the same principle as all that I've been looking at as orbit and planet, okay? All right. Do we have any questions? I see that we are 5 minutes into our extra time or spare times. Hello?
Sounds good.
Am I the only one in the class? How many persons do we have now? All right, so by next week, we'll start our discuss with the rotational motion, okay? And I'll upload what you'll be doing under this lecture 6, okay? Thank you all. Have a great weekend.
All right. Thank you.
Okay,
Bye.
bye-bye.